In this short lecture, I will give a brief introduction to the Brauer group. Let capital F be our base field. And we start with the following definition. Suppose that we have two central simple algebras, A and B. We say that A is Brauer equivalent to B if the n by n matrices with coefficients in A, it's isomorphic to the m by m matrices with coefficients in B, and this for some m and n integers greater or equal than 1. So it's a weaker notion than isomorphism. And a key remark is the following. So it turns out that every central simple algebra is equivalent, or it's Brauer equivalent to a crossed product F algebra. So this answers a question raised in the lecture about cross-product algebras. So it turns out that this remark is false if one replaces Brauer equivalent by isomorphism, and but under this weaker notion of isomorphism, the result is true. So it's quite natural to use, instead of isomorphism, this weaker notion of Brauer equivalence. So let's see some important facts. So suppose that we have A and B, two finite dimensional F algebras. And suppose that both of them are central. Then it turns out that implies that if one considers the tensor product over F, the tensor product is again central. Also, if they are both simple, the same holds for the tensor product. But if we instead consider if both of them are division algebras, then it's not necessarily true that the tensor product remains a division algebra. So this is no longer necessarily true. And so if one wants to introduce tensor products, it's better to use central simple algebras instead of division algebras. And another important fact is that if we have matrices, n by n matrices with coefficients in A, and we tensor them over F with m by m matrices with coefficients in B, we get something that is isomorphism to matrices of size n times m times n times m with coefficients in A tensor B over F. And so using these two facts, we can actually define the Brauer group. So the Brauer group, which was introduced by Brauer in 1930. It is defined as follows. So the Brauer group of F, what shall we do? Well, we consider central simple F algebras. We consider all of them, and then we mod out not by the isomorphism equivalence relation, but by the Brauer equivalence relation. And it turns out that thanks to the above facts, the tensor product gives rise to a well-defined monoid on this set, which is moreover unitole, and the unit is given by the base field. So we end up with a monoid. So if we have a notation, suppose that we have a central simple algebra, so this square brackets means the corresponding Brauer class in the Brauer group. So what's important here is that it's not just a monoid. When you mod out the Brauer equivalence, it's in fact a group. So that's the key remark, is that this construction gives rise to a group, to an abelian group. So let's write it in additive notation. So the sum of two elements is by definition the class of the tensor product. And one observes that the symmetric of an element is actually given by the class of opposite algebra. Why is that true? Well, if we have A, we can tensor it with its opposite over F, and then there is this canonical map towards the endomorphisms of A seen as a vector space over F, which sends an element here, A tensor B, to the endomorphism that to C it assigns ACB. So this canonical isomorphism, this canonical map, it's an isomorphism. And then you see that this right-hand side, so if you choose a basis for A, seen as a vector space over F, that is isomorphic to matrices of size dimension A by dimension A with coefficients in F, and that is Brauer equivalent to F. So that's the identity, the unit. So this is why every element admits an inverse, and we actually get a group when we mod out by Brauer equivalence. So important remark here. So as if we recall the Ederburn theorem that we saw in this lecture about central simple algebras, it implies that one can consider the Brauer group of the field, and the Brauer group it's in one-to-one correspondence precisely with the central division F algebras, and but up to isomorphism. So if we recall, we have this open problem of trying to classify central division algebras up to isomorphism. That turns out to be the same thing as computing the Brauer group. Well, let's see some examples of Brauer groups. So suppose that the base field is the complex numbers. So in that case, we already know that the only central division algebra over C is C itself. So in this case, the Brauer group, it's trivial. It's trivial in many other cases. So suppose that the base field is finite. So again, in this case, the only possible central division algebra over the field, it's the field itself. And this, it's actually, as a name, it's called the Ederburn little theorem. But there are, of course, cases where the Brauer group is interesting. For example, over the reals. Over the reals, we saw that there are two central division algebras over R up to isomorphism. It's R itself, of course, and then the other one is the quaternions of Hamilton. And then we also saw that the quaternions have this property of being isomorphic to their opposites by sending a quaternion to its conjugate. And then that implies that, in fact, the symmetric of the class of the quaternions, it's the quaternions themselves. So we actually conclude that this group is Z mod 2 in additive notation. Well, let's see a more sophisticated example. So let's consider the case where the base field is the p-adic numbers. So in this case, it turns out that one can actually compute the Brauer group, and all the elements of the Brauer group are going to be given by cyclic algebras in this particular case. So which algebras are these ones? So we can consider cyclic Galois extension, which is this one, QPN. Then we can consider the Frobenius. Then we can consider PM. So we get a cyclic algebra. We can consider its Brauer class. And this is parameterized in M and N, where the quotient is mod Z. So let me try to explain what are those things. So here, this field extension, what we do is that we add to the QP, to the primitive root of unity of order Pn minus 1. So this is what is usually called the unique unramified extension of the p-adic numbers of degree n. Then how about the Frobenius? It turns out that the Galois group of this field extension, it's isomorphic to the Galois group between finite fields. So going from Pn to P. And this Galois group, actually here, there is a canonical element, the Frobenius, which sends an element, it raises it to the pth power. And these algebras, when they are tensored, they give rise to the following structure, and we get that the group is Q mod Z. So in conclusion, the Brauer group of the p-adic numbers, it's actually all the roots of unity. So it's a quite large group. There's a lot of information. There are many central division algebras over the p-adic numbers, which are non-isomorphic to each other. Okay, so let's finish with some interesting remarks. So let's see. Recall that whenever we have two invertible elements of our base fields, we saw that we can consider the associated quaternion algebra, and this algebra has this property of being isomorphic to its opposites. But this is not specific to quaternion algebras. We saw that this also occurs whenever you have a quadratic form, which is non-degenerate. Then we saw that we can consider the following cases. So whenever the dimension is even or odd, we saw that the corresponding central simple algebra, in this case, the Clifford algebra of the quadratic form, or the even part of the Clifford algebra, they are isomorphic to their opposites. So in conclusion, we know that the Brauer classes of the quaternion algebras, but also the Brauer classes of this Clifford algebra, or even the Brauer classes of the degree zero part of the Clifford algebras, they all belong to the Brauer group of the base field, of course, but moreover, they belong to this two torsion part of the Brauer group. So two torsion subgroup. So it's difficult to understand the Brauer group, but the two torsion subgroup, one can say something about it. Namely, there is this famous result of Merkurev and Suslin. So a result from 1982 that says that this group, so the subgroup here, the two torsion subgroup, so two Brauer group of F, it's actually generated by quaternion algebras. So it's not true that every central simple algebra whose Brauer class belongs to the torsion group, it's isomorphic to a quaternion algebra, neither that it is isomorphic to a tensor product of quaternion algebras, but what the theorem tells us is that it's necessarily Brauer equivalent to a tensor product of quaternion algebras. So a quite remarkable result. Okay, thank you for your time.